When you first learn to fly, whether in a real airplane or in a flight simulator, you're taught that trim is there to reduce the force you have to hold on the yoke to keep the airplane steady. You'll often hear it described as a kind of poor man's autopilot. That description works well enough in practice, but what's usually missing is an explanation of how trim actually does that. And I don't mean how the trim tab behaves to change the forces on the elevator. That part is usually taught quite well. I mean what trim is doing underneath the surface in terms of forces, moments, and stability, and how that ends up affecting pitch and airspeed. In this video, we're going to unpack what's going on at that more fundamental level. Understanding this won't change the procedures you use in the cockpit, but it will deepen your understanding of why those procedures work. And if you're the kind of person like I am who keeps asking, yes, but why, when given an instruction, then this video is for you. Trim's main practical purpose is to relieve the force you have to hold on the yoke to maintain a steady equilibrium. Reduced yoke forces matter for a couple of reasons. First, fine control. It's much easier to make small, precise corrections when your hands aren't already loaded with constant pressure. Going from a lot of force to slightly less force is hard to do accurately. This becomes especially important during landing, where small pitch changes directly affect glide path and approach speed. Second, workload reduction. Instead of constantly attending to holding an exact force, the airplane tends to remain stable or drift only slowly. That's the limited sense in which trim is often called a poor man's autopilot. This episode is about the mechanism, what trim changes and why it works, and what it's actually doing in the airplane. The goal is to explain the conceptual foundation behind the procedures you're taught, at a level of detail that's rarely included in training materials. Trim doesn't add a new primary control to the airplane. It's a secondary control, and airplanes don't have to have it to fly or be controllable. It doesn't replace the yoke. What it really changes is where the steady control forces come from. Here I'm focusing on pitch trim, but the same idea of force balance applies to roll and yaw as well. Different airplanes do this in different ways. Some, like the Cessna 172, use a trim tab that creates an aerodynamic force on the elevator. The trim tab is a small surface on the elevator that deflects opposite the desired elevator movement. When the trim tab deflects, airflow over it creates an aerodynamic force that pushes on the elevator. That force doesn't move the airplane directly. It changes the hinge moment on the elevator. That can leave the elevator sitting at a steady deflection, but trim isn't locking it in place the way, for instance, flaps do. It's just changing the force balance. That in turn changes how much force the pilot needs to apply at the yoke to hold the elevator in a given position. The key idea is that the trim tab isn't commanding pitch. It's creating a steady aerodynamic force that biases the elevator. So your hand no longer has to supply that force continuously. But that's not the only way to do this. For example, a Cirrus SR-20 doesn't use a trim tab at all. Instead, it uses a spring cartridge in the control system. A switch on the side yoke drives an electric motor that changes the spring preload, which changes how hard the controls push back in your hand. The hardware details can vary. The underlying idea does not. Trim creates a steady force so your hand doesn't have to. Here's a useful way to picture trim from the pilot's perspective. Imagine your hand holding the yoke in a steady position. Now imagine a spring attached between the yoke and your seat. That spring pulls with a fixed force. Adjusting trim tightens or loosens that spring. Once you stop trimming, that force stays exactly where you left it. You can change the airplane's pitch by cranking on that spring, but it's an indirect and coarse way to do it. And that's why pilots are taught to use the yoke to set pitch first and trim only to relieve the force afterwards. If you watched my earlier stability episode on this channel, this should sound familiar. Trim doesn't exist outside the airplane's stability system. Trim interacts directly with it. Stability is fundamentally about what are called moments, forces acting at a distance. The airplane's pitching behavior depends on the net pitching moment about the center of gravity, and that moment varies with the angle of attack. This brings us to the core concept of what's going on aerodynamically. Now there's a bit of theory here. This goes beyond what's normally taught in ground school. It's closer to what's taught in undergraduate aerodynamics. There's only a small amount of math though, but the ideas are conceptually dense. I'm including this because it's what made trim and stability finally click for me. If this isn't your cup of tea, feel free to skip ahead. I'll return to practical implications shortly, I promise. There's one key diagram that makes all of this fit together, the pitching moment versus angle of attack curve. We'll use this to explain exactly what trim is doing and how it relates to the angle of attack. Before looking at it, a couple of definitions. The chord line is an imaginary straight line drawn from the leading edge of the wing to the trailing edge. You can think of it as the wing's geometric baseline. Angle of attack is defined using that chord line. It's the angle between the chord line and the oncoming airflow. It describes how the wing is meeting the air. Angle of attack is about orientation relative to the airflow, not relative to the horizon or the ground. In a wind tunnel, we can measure a pitching moment. That's a twisting torque that depends on the airspeed, air density, and size of the wing. By itself, that raw moment isn't very useful. It changes just by flying faster or building a bigger airplane. So instead, we define a dimensionless quantity called the pitching moment coefficient, or C sub m. C sub m still represents the tendency to pitch nose up or down, but it intentionally factors out size and airspeed. That lets us focus on the aerodynamic behavior of the design itself, the shape of the wing, the airfoil, and how the surfaces work together. Because of that, we can test a small model in a wind tunnel and measure its C sub m, and know that a full-size airplane with the same shape will behave the same way. Now let's look at what happens when we plot C sub m versus angle of attack for a statically stable airplane. This picture is most meaningful at the relatively low angles of attack we spend most of our time flying at. Once you get near stall, the aerodynamics become nonlinear and this simple relationship breaks down. But in this graph, two things matter. First, the negative slope. Imagine the airplane flying at a trimmed angle of attack. Now something disturbs it, a gust, turbulence, or a small control input, and the airplane pitches slightly nose up. That rotation changes the direction of the relative wind seen by the airplane. As we saw in the stability episode, because the tailplane is deliberately set to operate at a negative angle of attack in trim, that change in relative wind alters the tail's effective angle of attack in a way that enhances stability. It's actually pretty cool. The resulting change in aerodynamic force at the tail reduces its nose-up contribution and creates a restoring nose-down moment about the center of gravity. Instead of letting the pitch diverge, the airplane naturally rotates back towards its trimmed condition. That restoring behavior is what we mean by longitudinal stability. On the C sub m plot, which describes the behavior of the airplane as a whole, not just the tail, this appears as C sub m decreasing as the angle of attack increases. If the angle of attack decreases instead, the opposite happens. The aerodynamics produce a nose-up pitching tendency. The airplane is pushed back towards its original condition. The farther you disturb the airplane from equilibrium, the stronger the restoring moment becomes. That's negative feedback. That's static stability. The second important feature is the zero crossing. This is the point where C sub m equals 0. At that point, the net pitching moment about the center of gravity is 0. That point corresponds to the trimmed angle of attack. At that angle, the airplane is in balance. No continuous control force is required. Trim in this framework is simply the act of shifting that zero moment point. It sets the angle of attack the airplane is stable around. Changing trim doesn't change the slope of the curve. The airplane is still just as stable. What trim changes is where the balance point occurs. Trim doesn't hold pitch. Trim doesn't hold altitude. Trim doesn't directly control airspeed. Trim changes the equilibrium angle of attack. Once that equilibrium is restored, the airplane settles into whatever pitch attitude is required. With this understanding in place, we can now make sense of phrases pilots hear all the time, like pitch for airspeed. Airspeed plays a central role in how all of this shows up in the cockpit. For a given configuration, there is a specific angle of attack where the airplane is in equilibrium. That equilibrium angle of attack corresponds to a particular airspeed. That's why pilots often say the airplane wants to fly at its trimmed speed. What that really means is that the airplane is constantly trying to restore its trimmed angle of attack. This is why instructors often say the airplane is trimmed for a particular airspeed. That's a useful shorthand. What's actually happening is the airplane is trimmed for the angle of attack that produces that airspeed. Pitch changes angle of attack. Airspeed is the result. Now let's look at what happens when you change power. This is where many pilots get confused. I know I did. Imagine the airplane is trimmed, stable, and flying at a steady airspeed. Now you add power. From here on, it helps to separate what happens immediately from what happens after the airplane has time to settle. Initially, thrust increases. The airplane accelerates. Airspeed increases. During this short-term response, trim hasn't changed. The airplane is still trimmed for the same equilibrium angle of attack. Lift increases. That changes the force balance. The airplane begins to climb. As it climbs, the flight path tilts upward. Airspeed naturally decreases again. Over the longer term, stability restores the original equilibrium angle of attack, and with it, roughly the original trimmed airspeed. After everything settles, the airplane is flying at about the same speed, but now at a different climb or descent rate. This is also why putting a more powerful engine into an airplane doesn't usually change the airspeed it climbs at. The airplane is still trimmed for the same equilibrium angle of attack. So once things settle, it naturally flies at about the same speed. What the extra power changes is how much excess energy is available, which shows up as a higher rate of climb, not a higher climb airspeed. Pitch controls angle of attack. Angle of attack determines airspeed. Trim sets the equilibrium angle of attack. Power determines how much energy is available. This works so reliably because the airplane's natural long-period motion trades speed and altitude while holding nearly the same angle of attack. That energy shows up as climb or descent once the airplane settles. That's why pilots are taught, especially on approach, pitch for airspeed, power for altitude. On final, you trim for your target approach speed. If the airplane drifts fast or slow, you correct with pitch. You're directly changing angle of attack. If you're high or low on the glide path, you adjust power. You're managing energy. Once the airplane settles again, aerodynamics do the rest. Trim sets the angle of attack the airplane wants to fly at. Pitch moves you toward or away from that angle. Power determines whether the airplane climbs or descends while doing so. I first encountered these ideas in Stick and Rudder by Wolfgang Langewiesche. It gives an excellent intuitive picture of what to expect, but I was left asking why. The FAA's Pilot's Handbook of Aeronautical Knowledge goes further, but trim didn't fully click for me until I looked directly at stability and control theory, especially the C sub m versus angle of attack graph. Once the role of moments and equilibrium became clear, everything snapped into place for me. But you don't need to understand any of this to be a good pilot. Training quite reasonably focuses on the procedures that work. This video exists so that when you hear trim advice later, it doesn't feel mystical or contradictory. It has a physical explanation underneath it. If you found any of this useful, please consider liking and subscribing. It really helps my channel grow. Thanks for watching, and happy simming.